Okay, here's a unit conversion example. It says an owl is able to drop a distance of 1.30 meters in 0.8 seconds to capture its prey. Determine the owl's average speed during its descent in kilometers an hour. So they give us it in meters per second. So this is its meters per second number. And what I'm going to do here is just figure out what that actually is in meters per second. So we do need to divide those two numbers. 1.30 divided by 0.8 will give us our meters per second. So it's 1.625 meters per second. So that's pretty fast. So let's convert these. Our first method, they're giving us two methods that we're going to use. The first method is converting meters to kilometers and seconds to hours before calculating your answer. So this step or this way of doing it is a little bit longer. I think it takes a little bit longer, but it's whatever you can see in your head. So what I'm going to do is we'll start out with 1.30 meters. And we're going to change that into kilometers. So what I want always goes on the top. What I want to get rid of is meters. So these will be on the bottom to cancel that out. And we need to do a conversion factor. 1 kilometer is in 1,000 meters. And you can see that on the previous slide. So when I do this calculation, I get 0.0013 kilometers. Okay. And then next we will do I guess I should do this in a different color. And then we are going to convert our seconds. So a conversion factor as well. Seconds is on the top, so we want it to be on the bottom. We're going to hours. In every hour, there's 3,600 seconds. So if we do that calculation, we get an answer of, I'm going to put it underneath, 0.0002. This is repeating. Okay, and that's hours. All right. So then we have those two numbers, so now we can calculate it. We've got our kilometers and our hours, so it's always kilometers over hours. So we take our kilometer number divided by our hour number. And when you do that out, you get 5.85 kilometers an hour. That is really awful. Okay. 5.85, that's what we get for our answer. So that is your one way of doing it. Underneath, we're going to try a different way. So calculate the answer in meters per second, which we've done up here. So I've done the division. Then use unit analysis to convert. So I'm going to do this right here. So we got an answer of 1.625. That's meters over seconds. Now we're going to do a couple conversions, sort of just like we did, just all in one step. So we've got meters on the top, we need meters on the bottom. We got seconds on the bottom, we need seconds on the top. We want to go to kilometers per hour. In 1 hour, we have 3,600 seconds. In 1 kilometer, we have 1,000 meters. So I'm doing it like this because my seconds are on the bottom, seconds are on the top, they'll cancel, meters on the top, meters on the bottom, and then we'll be left with what we need. How we would calculate this out is I will multiply across the top and then multiply across the bottom. So if I take my 1.625 and multiply it by 3,600, I get 5850 on the top. And if you have a calculator that you could do this all in one step, go for it. And then on the bottom, I just have 1,000. Well, 1,000 times 1. So I'm just multiplying across the top, multiplying across the bottom, and then once I've got those two answers, I'm doing the division. If we take 5850 divided by 1,000, we are going to get 5.85. That's kilometers an hour. And if you note, it's exactly the same as above. So same-ish thing, just in some more steps. You still come out to the same answer. So it's up to you on how you want to do this. But do what works best for you or whatever you think makes sense to you. Okay? Average velocity is next. So it says if you want to know how fast an object is moving, the average speed of the object is useful. However, average speed does not reveal anything about the direction of motion. So if I told you I was going 100 kilometers an hour, you'd be like, okay, great. But I'm not telling you any sort of direction I'm going. You would have no idea the context of it. When we talk about velocity, velocity always has a direction. So this velocity, it has to have a direction. So it's the exact same formula that we used. V is equal to d over t, except for you got these little arrows over top, and that arrow is signifying that there's a direction that we're going. If you look at these cars on the right hand side, you'll see that the speed is 25 meters per second, but the velocity is different. The velocity for the car on the top is going in a negative direction, and the bottom is a positive. I'm just going to write down sort of how we calculate that. If you remember in math, if we had a chart or a graph like this, everything in this quadrant or to this side is positives. Everything over here is negative. Down is negative and up. Well, I shouldn't put it there. Up is positive as well. Okay, so see that this car right here, it's going to the left. So if it's going to the left, it's got a negative direction. This one's going to the right, so if we look at our coordinates, yeah, it's going in the positive direction. Another thing to note is sometimes we don't use positives and negatives. We actually use like compass coordinates. So we use north, east, south, and west. So we can also, on these cars, we can look at them and say, oh, they're going, they are going a certain direction, not just negative and positive, but we can also say that this car is going west. We sort of put these square brackets around it. And then this car here would be going east. Okay. So that's how we look at direction when we're talking about velocity. As far as displacement, so displacement is a little bit different than distance. Distance is like how far you went from where you started Displacement, on the other hand, is how far you end up from your original location. So my example I always tell people is that I leave my house in the morning. I go to school, so I'm going to say my house. And this is the school. And then at the end of the day, so I'm going there at the first of the day. At the end of the day, I go back to my house. If we're looking at my total displacement in the whole day, well, my displacement is 0. And the reason why it's 0 is that I never went anywhere. Well, I did go somewhere, but where I started is where I stopped. So wherever you start and stop, you're measuring the distance between where you started and stopped. So in this case, I started and stopped at the exact same place, so my displacement is 0. Okay. We'll do an example, I guess, on the next slide. Or maybe it'll show you how to calculate it. So when displacement is calculated, it is convenient to assign a sign of plus or minus to each direction. So if we have north, then we are going to put a positive. If we have south, then we're going to go negative. And then I guess I can do, if we have west, it's going to be a negative. And east is a positive. Okay? So whenever we see those northeast, southwest, we can just put, instead of putting the W, N, E, and S, we're going to put signs. Because we can calculate this with this pretty easy formula. Or I guess it's not even a formula. You just have to add all of your distances together. And as long as you have the signs, you'll figure out your displacement. So for example, if a vehicle travels 50 kilometers south, so south, look at it right here, it's a negative sign, so we've got 50 kilometers south, and then turns around and travels another 75 kilometers north. North is a positive sign, so we've got the positive sign right there. What is its total displacement? So how you calculate that is literally this, so negative 50 plus positive 75. And we get an answer of plus 25, or we can put 25 kilometers north. Do not put plus 25 kilometers north, because that is sort of like two positives together, or two negatives that can cancel each other out. We don't want to have both of these, so you choose this or this. It's up to you unless the question says like you need a certain one. Okay? So, how we calculate it is what we showed you on the other slide. We can also draw pictures, and this is what they're showing you on this sort of number line. You don't have to have a number line to draw a picture. For me, if I was reading that question, I would like put a starting point, if I can. Read the question. So if a vehicle travels 50 kilometers south, so I would draw an arrow down and write 50. And then turns around and travels another 75 kilometers north. What is the total displacement? So really, the displacement is the time between here and here. So that little chunk. And basically it's just maybe I can see it better in my head that way. This number line shows you exact numbers. So it's telling you, well, that distance between here and here is 25. But I like to draw that picture and then do the math. Like my picture that I have at the top here. Just because in my head it makes more sense. And it's whatever works for you. So if you're maybe a visual learner and you need to draw a picture, draw a picture. If you don't, you just want to do the math, just do the math. So if John walks 2.6 kilometers north to school in the morning and returns home along the same path in the afternoon, what is John's total displacement from his house at the end of the day? This is the exact same thing as my example, but we'll do it with numbers. So he walks 2.6 kilometers north. We want to put a positive because that's what north is. Plus, and then he comes back the same direction at the end of the day. Or sorry, he comes back the same path at the end of the day, opposite direction because he's going back south to his house. So if we add those two together, we get 0 kilometers. So his displacement is 0 because he started and stopped in the exact same spot. If we have another one, it says if John walks 2.6 kilometers north to school, 2.6 kilometers north to school in the morning, and another 0.2 kilometers north to his friend's house after school. Make sure to put that plus sign. To his friends after school, what is his total displacement from his home at the end of the day? So it never says that he goes back, so we're just going to add these two together. So 2.6 plus our positive 0.2 would give us 2.8 kilometers. You can write north if you'd like, or you would just write 2.6 positive. It's up to you. Okay? So this is our answer. And then the final one, it says John walks 2.6 kilometers north to school. So he again is doing that positive 2.6 kilometers. After school, he walks 3.8 kilometers. South. So south is a negative number. He walks there to his work. What is his total displacement? So this one, we add 2.6 plus negative 3.8. We're going to get a difference of negative 1.2 kilometers. You can write that, or you could write 1.2 kilometers south. Okay, so up to you again how you write it. I really prefer this way, personally, just because you don't have to really think about it, but up to you. And the question might ask you to use direction, like southeast, northeast, southwest, so you might need to know how to do that. How we would calculate average velocity. So we need to do some questions that involve this. So it says, now that you know how to calculate displacement, you should be able to determine the velocity of an object. Recall that velocity can be calculated by dividing an object's displacement by the amount of time required to travel that distance. So that big thing about difference between speed and velocity, this is our displacement. I'm just going to write displacement. So that D on the top, that delta D with the little arrow, that's telling us it's our displacement. So let's try calculating a velocity. A vehicle travels 110 kilometers north. So that is a displacement with a little arrow. And then they turn around and travel another 24 kilometers. I'm going to add it. South, if the entire trip takes 1.2 hours to complete, so a time of 1.2 hours. What must have been the average velocity of the vehicle? So we've got some pieces of information here. I'm going to actually write this differently. I wrote it down right how it is in the question, but I'm going to write it a little bit differently because I like to put the signs like we did on the last slide so that we can figure out the displacement really easily. So it says 110 kilometers north. So north we know is being a positive, so I'm going to put that there. Plus 24 kilometers south. So south is a negative number. So if we add those two together, we should get our displacement that we're going to use in our formula. So we go 110 plus negative 24, and that gives you 86. Okay, so 86 kilometers. We've got our t. Now we can plug that into our formula. So our formula is v is equal to d over t with a little arrow. We are going to plug in 86 kilometers. That's going to be a positive because it is a positive. So we got to keep that direction in there. Divided by our 1.2 kilometers. Or sorry, hours. What am I saying? So if we take 86 and divide it by 1.2, we will get 71.666. 6 repeating. And that is a velocity, so that is in kilometers an hour. And we need to have the direction, and the direction is positive. Okay, so when we do that out, it equals positive 71.6. That's repeating in its kilometers an hour. All right, so not much different than when we were calculating speed, but we're just needing to do that displacement first. So just figuring out those directions and the positives and negatives so that we can figure that out. Let's do the bottom one here. It says a soccer player kicks the ball forward 9.5 meters to their teammate. So this is another displacement question, or it's an average velocity. I'm going to write my little displacement with an arrow. And I'm going to write down this first number. So they say 9.5 meters forward. Forward is always in a positive direction. So I'm going to write positive 9.5 meters. Okay? To their teammate, who then directs the ball another 5.3 meters forward into the net. So we add another 5.3 meters forward. If the ball reaches the net in 4.3 seconds after being kicked by the first player, what is its average velocity? So we've got a displacement, we've got a time, 4.3 seconds. I want you to know it's a S for seconds, but it still looks not great. So we need to calculate the 9.5 plus the 5.3, and that gives us 14.8. Remember to always put that positive there. And that's 14.8 meters. Now we can use our formula. V is equal to d over t. And I'm going to put 14.8 divided by 4.3. 3. So if I do that out on my calculator, that will give me my average velocity. I do that out on my phone and I get 3.44. Space is not my friend here. I'm going to erase this just temporarily. Just going to go V is equal to 14.8 divided by 4.3. And then we can put our answer in as 3.44, and that's meters per second. Okay? So this is our answer. 3.44 meters per second. And this is our answer over here. Just so we're highlighting those answers. Okay? So that's how you do average velocity. There's still more questions. I'll do one more of these as an example, and then I'm going to continue on just because I know that it'll be a lot to watch these videos. It says a cyclist travels at a velocity of 23 kilometers an hour west. So I'm going to do this middle one. What will be their total displacement after a period of 25.25 hours? So we've got a velocity, 23 kilometers an hour, and that's west. When I'm writing this, I like to not worry about necessarily the west part, but put that into as a sign. So just a refresher over here, north, east, south, west. So if I'm doing west, west would be in the negative direction because it's this way. So I'm going to put a negative there. What will be their total displacement after a period of, so are they giving us a time of 0.25 hours? Okay. So using our formula, we've got to rearrange it so that we can solve for our displacement right there. So to do that, we're going to bring that t up to the top, multiply both sides by t. I'm just changing the formula before I even plug it in. So our formula ends up being t is equal to v times t. So if we're plugging ours in, we would go negative 23 kilometers per hour multiplied by the time, which is 0.25. This is multiplied just so you can see. And when we do that, I'm going to write the answer over here. So 23 point nothing multiplied by 0.25, and that's 5.75. That's a displacement, so the displacement is measured in kilometers, and it is a negative because it's going to the west. All right. So that is our answer for this question. Sorry, I had to go backwards. But again, remember, we're just using that simple formula of v is equal to d over t if you're solving for v. If you're solving for d, it would be v times t. And if you're solving for time, then it would be d divided by v. So you can rearrange those formulas. I'm rearranging it for you right now. And that's what you would use to solve for your missing piece. Okay? So graphing uniform motion, it says position versus time graphs allow us to compare the velocity, speed of objects moving in a uniform manner. So if we look at a graph of distance over time or position over time, which is the one you see on the left-hand side here, this is a position time graph, and it can show uniform motion. So if it's in a straight line, we know it's uniform. A velocity time graph allows us to interpret the displacement of objects moving in a uniform manner. So if we have our velocity on the side and then our time on the bottom, that's like a distance or displacement is equal to velocity times time, and we can see what the velocity it is over time. So something that's uniform in this type of graph would be a straight line, and something that's uniform in this type of graph would be a upward line. Okay. Like I said before, uniform isn't really something we see in life, but something that we can see when we're dealing with these types of questions, possibly. Explain what's happening in each of the following position time graphs. So if we look at this position time graph on the very left, the position is staying the same over time. So this person is not moving. Because their position is not changing. They were at this position and they're still at this position over time. So they're not moving. The next one is definitely a uniform motion. I'm just going to write it up here. So that one's uniform, this one not moving. This is uniform because it's in a straight line, it's uniform, it's moving, and I guess we can also say that it is going in a positive direction. Because it's moving, I guess, away from its starting point. The next one is also uniform. But it's in a negative direction. So it's going downwards over time. It's going back or away from, back towards its starting point. And then the last one, position time graph. This is not uniform. They're speeding up. So this is not for uniform, it's speeding up. It's also in the positive direction. Okay. So this is something that you need to know. You need to know how to look at these graphs and decide what's going on. So straight line across on these types of graphs means, on a position time graph, that you're not moving. A line upwards straight is uniform in the positive direction. A line down is uniform in the negative direction. And then the next one is not uniform, but it is something that would be speeding up. So its position over time is moving in an exponential direction. So yeah, it's speeding up. This is similar to what we would see for our COVID cases. Interpreting a velocity time graph. So this is a little bit different. So its velocity, or its speed, we should say, over time. So this is going at a constant speed. Because its velocity's at the same part over time. So it stays over time. And this has nothing to do with where it is in position. It's just looking at its velocity. So this is someone who might have like cruise control on their car. They're staying at the constant speed. This one, next one, they would be speeding up because as time goes on, their velocity gets larger, right? This is a larger velocity as you go up, so this would be speeding up. And then the next one, hopefully you have a good guess that if your velocity is going down, you would be slowing down.